Thanks for joining me today. I'm going to be talking a little bit about our new database project and about how to keep your data alive using harmonized repositories. My name is Edward Davis. I'm a curator of fossils at the University of Oregon Museum of Natural and Cultural History and an associate professor of earth sciences at the University of Oregon. So most biological data are already dead. I think if you really looked at the history of biological data collection, there's a lot of data that are in formats that are no longer readable, have been destroyed with people's retirements, otherwise not kept. And so a lot of the data that have been collected have already been destroyed. And it reminds me of a phenomenon about the history of life. It was pointed out by Raup in 1991, and that's that most species are already extinct. When you look at the proportion of extinct species to living species today, it's overwhelming. And I feel like the same thing's been happening to biological data, but it doesn't have to. And in fact, unlike species which stay extinct, we can actually resurrect some of these data and make them available again today. So this is what I'm talking about, is trying to reverse these proportions and keep all the data alive. Data aren't like species. They don't have to go extinct. A lot of papers, especially older papers from the history of biology and paleontology, but even some current papers, present only their data as summary statistics or scatter plots in the paper. And I just picked two at random from my PDF stack. But what you're seeing is that basically for these papers, the only record that you have are the mean values that are presented in the summary statistics table, or a scatter plot of values, which you could try to reconstruct into original values by using something like Fiji, but is not going to ever get you back to the actual observations that were made to produce the plot in the first place. That's not cool. If the original data that underlie those papers are lost, then those papers just become anecdotes. They aren't really scientifically valuable in the same way anymore. They are stories that people have told that are probably reliable, but there's not a good way to check into them, rerun the analyses, and there's also not a good way to expand upon them by taking those data and including them in new analyses. Sometimes there are situations where data that you've taken couldn't be taken again. This is a paleontology example. There's a fossil site underneath the place where they've built the Matt Knight Arena at the University of Oregon campus. And there's no way we're going to be able to sample that site again. So we want to make sure that the data that were taken from that site are maintained in a way that's going to be available in perpetuity. And there's plenty of other examples out there, but this is one that's particularly relevant for me at the University of Oregon. If you have data presented in tables, it's a little bit better. The data original data values are there in a paper, but if you're going to use them for anything now, you have to rip them. So if it's in a PDF, there's some ways that you can do that in a semi-automated fashion using optical character recognition. But if it's if it's not perfect, or the typeface is an unusual one, you're going to end up having to rekey it. Anytime that you're rekeying data, there's always opportunity for additional keystroke errors. If you're using OCR, there's an opportunity for errors to creep into the data too. So it's better not to have to transcribe the data in that way. And so nowadays we do have the opportunity to record the original actual data tables with your paper and put them in places that are publicly available, places like Dryad, so that you can have those data discoverable. But the only way you can discover the data really is through the papers, and then you still have to extract the data. You have to reorganize them and understand what the values represent, and then you have to clean them again. So there's a whole additional process of taking someone's data set that's from Dryad and being able to incorporate it in your own data set. And a lot of that has to do with human work of aligning data fields. And that's something that computers can actually do for us. So that's where we're going to get to. So if you put your data into a harmonized repository and not just a data dump repository like Dryad, it keeps the data alive. It's not just present in this kind of twilight of life, but it's actually vibrant, like the blooming flowers here. And so there's a number of places where you can put data like these today. GenBank is one of the best examples. It's a great place to find data. You don't have to go to the original papers to discover the data. It's got a lot of good resources for discovery on its own. It has DOIs to track the sequences so that people's use of your data gets you citations even if they don't use the original paper that you published. And the data are always kept in the current format, so NCBI is continuing to update and keep GenBank relevant. Similarly, for paleo data, there's a couple of different places you can put data, the paleobiology database and the Neotoma database. And they're working to keep the data relevant, keep it available, make it easy to discover. I'm a collaborator with the Neotoma database, and we're in the process of doing some of that work to make sure that our backend stays current so that the data will be continuously available. And similarly for geochemical data, there's the EarthChem database. And so what we saw was that there's a gap here for trait data, for the measurements that we do in all kinds of integrative biology research. And so that's what FuTRES provides. It's a trait database. It stands for Functional Trait Resource for Environmental Studies. And the idea is that you can use the data in FuTRES to study how organisms adapt to the environment either through time or over space or across both space and time. It's focused at the specimen level, so we're not just looking at average trait values for species. That's what you can get mostly on the internet right now and from other people's publications. So it's going to be a massive resource for looking at specimen level data, so you can look within species for clines, time and space. It focuses on measurable traits, so that these are things that you can measure about an organism, but measurements go a lot of different ways. You can actually get to the point of including color as a measurable trait. The primary focus right now is on vertebrates, and in fact we're strongly focused on mammals, but we do have bird data that we're incorporating, and eventually we want to expand this database so that it functions for all kinds of animals. And there's a similar effort on the way for plants that we're going to try to integrate with, so that eventually there will be trait resources for animals and plants of all kinds, and even microbes. But right now, focusing on vertebrates. And the thing that really makes this important and useful and cutting edge is that we're ontology based. So instead of just having a set of data tables so that we're putting trait values into fields that we've already created, we're actually organizing the data in a completely different way that's focused on the anatomical connections within organisms, and that makes the database infinitely extensible. Okay, so what is an ontology? An ontology is a way of representing ideas and the connections between them in a computer using kind of a graph theory system. And here's a really sketchy example that I'm going to explain with my limited understanding, but I've been told that this is pretty close to what's going on. So you might have a specimen as an object in the database, and that specimen might have, let's see if I can get it, it might have a mass, and then the mass might be 10. So, okay, so you're connecting two nouns with the verbs, the specimen and 10, and you're just connecting with the has the mass. Okay, so that's the basic idea of ontologies, is you've got a subject-verb-object connection, and the computer understands what the subject, the verb, and the object represent through graphing them, connecting to other concepts. So it has a mass of 10, and that 10 has units of tons. So it's a 10-ton specimen, okay? And then that specimen also belongs to the taxon Elaphus maximus. So it's an elephant, an Asian elephant, okay? And then that specimen has the name Tusco. At this point, we're actually kind of localizing it. And the specimen is reposited at the Yo Museum of Natural and Cultural History. And so in this case, I'm giving the data that we would have in the graph system for Tusco the elephant, which you can learn more about on the internet if you want to. He's pretty famous and a pretty tragic life. But anyway, the idea is that by connecting all these ideas, you can look for any specimens that have mass values, but you could also look for specimens that have inferred mass values and compare those. And you can look for specimens that have, femoral length values. You can look for specimens that have, midshaft humeral diameter values. Whatever trait you can come up with, we can connect it to the ontology that represents the skeleton of a vertebrate, and then people can figure out how to find it. So you could say, I want to do a search for all specimens that have any kind of measurements on the humerus, and you get all the humerus measurements in the database. It's pretty powerful. So you don't have to worry about the data death of floppy disks, because the data are kept in a current up-to-date format. So as the database is used and shepherded, it gets updated and upgraded so that the data always are available. And then we're building it with APIs to link it to other repositories so that it'll be easy to discover our data if you're searching someplace like the paleobiology database or say iDigBio. There'll be links that let you go back and forth between these different data discovery resources. I got the ePanda logo up here just as an example of one of these efforts that's come to fruition. So the ePanda API is available, and it connects several different paleo databases together to make the resources easier to discover. And this is the direction that we're moving. It's what they call the Semantic Web, so that if you pull up a specimen record, it'll have links and the specimen record value on, say, iDigBio that would take you to records on FuTRES, or if you have discovered on FuTRES, it'll have links that you could take from that specimen to iDigBio or to the paleobiology database so you can find out more about that specimen. And these are all connected in such a way that computers can do it automatically, so you can build code in something like the R programming language to pull all these things together for you automatically. So we're trying to streamline the data discovery and alignment process so that scientists can spend more of their time on testing hypotheses and understanding the way the world works. Okay, so just to make it really clear, the idea is that when these resources are available, say FuTRES and its API connections to these other databases, then you'll be able to find data from a lot of different disciplines, and they'll connect together in surprising ways, right? Because FuTRES might connect to that AIDA geology database. And so somebody who's doing geomorphology research might find things that they need about ecological clines from FuTRES to help them with some question about the geomorphological system. Or some evolutionary biologist might interrogate FuTRES and then find a connection to some isotope data that are in AIDA, and that would help their evolutionary biology research. So this is the future that we're looking for, where all these different disciplines can help one another indirectly and also directly. So in the end, wouldn't you want your life's work to be available forever and not to go extinct? Please don't let your data die with you. Put it into some place like FuTRES so that it can be available indefinitely into the future. Thank you for your time.